Hi, welcome back. So we will be continuing looking into electric fields today. So quickly, last time we talked about electric field as similar to gravitational field. Um, the electric field, it can be calculated using E equal to K Q over R squared, so absolute value of Q, that gives the magnitude of the field. Now, the direction of the field depends on if you have the positive or negative Q at the source, if as your source. So if you have positive Q, then electric field is pointing away from the source. If you have negative Q, it's pointing towards the source. Okay. Um, so electric field can be also defined as the electric force divided by the charge of the test charge Q naught. So E equal to F over Q then. The SI unit for electric field is newtons over coulombs. Okay, so where Q0 is the test charge you use to test the electric field. So it depends on if you have a positive Q or negative Q, your force and field could be in the opposite direction or in the same direction. For positive Q, E field and force are in the same direction. For negative Q, E field and force are in the opposite direction. And again, if you have positive Q, electric field is pointing away from the source. If you have negative Q as the source, the electric field is pointing towards the source. For multiple sources, you add the field by each of the source charge. So summation of the electric field by individual one, okay, at your point of interest. If you have electric field presented, the motion of the charged particle then can be altered by that electric field. So the acceleration due to the electric force, you can calculate this total force divided by the mass, which is Q times E divided by the mass, okay? Today, we are going to look into the next two sections in this chapter. So first, the electric field line. So you have seen this earlier. So if we go like in this case, so lines are used to represent electric fields, and also here and here. So so this is one of the techniques we use to represent electric field. So they are not actual lines, but they help us to visualize the electric field. Okay, so for electric field lines, so there are four points here. The first one is they point in the direction of the field vectors at every point. Okay, so if you have the electric field line, then that represents the direction of the electric field vectors. The electric field lines, they start at positive charges or from infinity. So this is the case if you have charge in space, so they start from positive charge, okay? And if you have the negative charge, then they start from infinity and pointing towards the negative charge in that sense. If you have negative charge, so electric field will end at that negative charge, okay? And if you have positive charge, electric field actually will end at infinity. So starting from the positive charge and then ending at infinity in that sense. The density of the field lines represent the strength of the field. So if you have more dense lines at certain locations, so that means electric field at that location is stronger, okay? So for example, if you have just positive of Q here, so electric field line, they will start at the positive charge, okay, and then pointing towards the infinity or end at the infinity. And on the other hand, if you have a negative Q, in this case, minus 2Q, so electric field lines, they end at the negative charge, but they are coming from infinity, okay, in that sense. And for this, just positive of 1Q compared to minus of 2Q, so the electric field over here will be denser, so you have more electric field lines compared to this guy, okay? If you have couple charges nearby each other, for example, there are three scenarios here, positive and negative, so then field line will start at the positive charge and at negative charge, okay? And if you have like more charges, so if you do KQ, right, over R, so if Q is more, then you have stronger electric field lines. So in this case, over here, at a positive 2Q, you have more lines compared to the just minus 1Q there. Okay, so electric field strength here is stronger than here. If you have two like charges, they will actually repel each other. Okay, so then the electric field line shows up as repelling each other as well. Okay, so in the middle over here, you actually will have no electric field because the electric field produced by these two will cancel out. Okay, in the middle. So in the middle here, it's empty, so electric field will be equal to 0. All right, and then again, the field line densities represent the strength of the field, but in this case over here, okay, so you can see over here, this is more dense over here than compared to here. So you have field line stronger on this side than compared to over here, okay? All right, so you can simply actually count the number of the lines, okay? And then divide by the area to get the electric field line density in that sense. One example here, so this one asks the electric field lines surrounding 3 charges are shown in the figure. The center charge has the charge of minus 22.8 microcoulomb. What are the signs of Q1 and Q3? And find Q1 and Q3. Okay, so because the center one is minus, so field lines go into it. Okay, so that's why it's minus. Now Q1 and Q3, you can see field lines actually start from there and the arrow is pointing towards the negative line. Okay, so you can see signs of Q1 and Q3 should be positive because the line start from there, ending at the negative Q. Now finding Q1 and Q3, so Q1 over here, you can count how many lines are surrounding Q1. So there are 8 lines here, right? And then counting how many lines surrounding Q2. So on Q2, they are actually, if you count them all, 8 on one side, 8 on the other side, so 16 lines. So that means field is more stronger surrounding Q2 than Q1. So Q1 should have its 8 lines, so then it's half of 16 lines, so it will be just half of Q2, but positive. So that means it's 22.8 divided by 2 microcoulombs. Okay, so 11.4 microcoulombs on Q1. The same will be on Q2 because Q2 also just has 8 lines surrounding it, Q3. So then Q3 will be also equal to half of Q2, so but positive 11.4 microcoulombs. Okay, so the signs of Q1 and Q3 are positive, both positives. The magnitude Q1 is equal to 11.4 microcoulomb, Q3 is also equal to 11.4 microcoulomb. Okay. All right. The next section on electric dipoles. So the definition of dipole, electric dipole, is a system of 2 equal and opposite charges separated by a small distance L. That's called dipole. So they have to be close to each other. Okay. So and the dipole it's defined as, so we use symbol P for that, equals to Q times L as a vector. So that means a vector quantity, it is defined as pointing from negative charge to the positive charge, okay? And then with the length of the separation, okay? So dipole should have a SI unit of coulombs times meters in that sense, okay? And then it's pointing from negative charge to positive charge. So if you have a system of dipole, 2 charges separated by L, okay, placed into the electric field, so then there will be forces on the positive charge, there will be forces on the negative charge. So those two will be pointing in negative opposite direction, right? Because one is positive charge, the other is negative charge. So in that sense, you create then a torque on the object here, the dipole here, okay? Because one is pulling this way, the other one is pulling in that way. So then there's a dipole, or there's a torque there. So torque in this case is equal to P cross E, P multiplied by E. So it's force times the length, right? So length will be L, force will be equal to Q times E on each of them, and then with the X rotation at the center, so R will be equal to half of L for one of the charge, okay? And then for both 2 charges add up, they will be multiplied by 2. So it's going to be end up with Q times E times L, where Q times L is the dipole P, okay? So then P cross E. So then for the work done, by this torque over here should be equal to torque d theta, a derivative in the differential form, derivative of work equal to minus tau d theta. Okay. So and in this case, it's minus PE sine of theta, the derivative of theta, because for P cross E, the amplitude will be PE sine theta, okay, and derivative of that. So if you are looking for the change of the potential energy in this case, then it will be minus of the work done. So derivative of U equal to minus of derivative of W. So that gives you PE sine theta d theta, okay. All right. So then you integrate both sides of the equation to get the potential energy. So potential energy will end up in PE cosine theta minus, okay? So then that'll be minus P dot E, okay? All right. So in chemistry, like when we talk about molecules, right? So a lot of molecules will be having a dipole moment, okay? So that's then called polar molecular. So for like H2O water molecules, right? Oxygen is -2 charge, and each of the hydrogen is positive charged. So then you can think about this as the one positive, one minus. That's a dipole there in that direction, and then there's a second dipole plus charge and negative charge in that direction. So the resultant of these two dipoles as a vector add up will be in this direction. So that's the dipole in the water molecular. Okay. All right. Neutral molecules, that means they are initially the charges is not polarized, right? So they may have a positive and negative overlapping each other. That means the negative, for example, hydrogen atoms, molecular negative charges surrounding the positive nuclear. Now, if you place it into electric field, then you may make the molecular polarized. So then a positive charge will be attractive towards the positive source charge here, or negative will be attractive, and positive will be repelled. Okay, so it's moving away from there. So then there's a separation between these two. So then it makes that the dipole. Okay. All right. So it's called induced dipole. Let's take a look on this example here. It says, what's the dipole moment of the configuration shown here? FQ is equal to 4.0 microcoulombs and A is equal to 1.0 meters. And B, what's the torque on this dipole with the electric field of 4.0 times 10 to the fifth newtons over coulombs in the I direction? Okay. So to calculate dipole, we'll do, so P is going to be equal to Q times L, right? L is the separation of the two. So the charge is 4.0. Okay, so then this is equal to 4.0 microcoulomb. L, in this case, is pointing from the negative Q to the positive Q. So from the figure, you'll see that is 2 times of A, okay? And then in the positive I direction, so I'm going to call it J. So 2 times of A being 1.0 meters. So 2 times 1.0 meters in J direction. So 4.0 times 10 to the minus 6 times 2 meters, basically. So that gives you 8.0 times 10 to the minus 6, right? Coulombs meters in the J direction. So that's your dipole. Okay, it's a vector, so it has direction. All right, so now it's asking you what will be the torque of this dipole. So for the torque, it's equal to P cross E. Okay, so P is this guy, 8.0 times 10 to the minus 6 newtons coulomb, or meters times coulombs in the J direction cross. The E is given as 4.0 10 to the fifth newtons over coulombs, but in the I direction. Okay, so you can do this guy multiplied by that and J cross I. So we know I cross J is equal to K, right? So if you reverse the two, then that gives you minus K. So this will be equal to, this times that will be 32. And minus 6 and 5 will cancel 5, but leaves -1. So 32 times 10 to the -1, that means 3.2. Okay, 3.2 newtons. You have coulombs, coulomb cancel, but newtons times meters, and then minus of that times K. Okay, so that's the torque. Okay. All right. So let's move on. Go back to the slide. So we have been talking about electric field by point charges. What about the, you have a charge distribution, okay? So make it a bulk of charge. So then in that case, you actually divide the bulks into small pieces, okay? So small pieces, in this case, like cubic or whatever, small shape that could be. So then you are talking about, if you are looking at the electric field at this point P here, then you'll be actually calculating the electric field by this small piece, right? At that point. And then add up the next one and the next one and the next one, all through the whole body. Okay, so that's what you're going to do. So for the small piece, it's going to be differentiation of E, okay, equals to K dq, which is the Q in this small volume of rho times dV over R squared. I'll be from point of interest to that one. And then in the direction, radial direction from this one pointing in that one, that's the unit vector, okay? And you'll do integration through the whole body to calculate the electric field at this one by this charge distribution, okay? So there might be bulk charge distribution, there might be surface charge distribution. So you have sheet up whatever material, and you have charges distributed through the surface, the sheet of the sheet. Or you may have a line that has charge distributions, okay? Then, so for different shapes of charge distribution, if it's linear, we are going to use lambda for the linear density. So that means the total charge divided by the total length, okay? And for a sheet of charge distribution, you're going to do the charge Q over the area for the density. We call it sigma. So that's the refer to the surface charge density. For the bulk, we use the rho here. So that's volume density. Okay, so for different shapes. And for example, if you have sheet, then you are just taking a small area on the sheet called dA, derivative of the area. And then there's another one, okay? So then if you have symmetric, then that's what you're going to do. So there will be cancellation of that. You will see that nearby the surface of the sheet, then the E net will be in this direction, because this guy and this guy will cancel out in the X direction, but Y direction, they will add up, okay? So then the net electric field will be in the Y direction, okay? So we are going to examine those different scenarios one by one. Maybe not all of them today, but in today and the coming lectures, okay? So then just to summarize a little bit, for point charges, right? If you have several point charges, you do summation of electric field by each of the charge, okay, at your point of interest, P. For line charge distribution, then you integrate through. Okay, so dq in this case will be lambda times dl, okay, the small length on the line, and then over r squared times the directional vector there, okay. For surface charge distribution, your dq will be sigma times dA, okay, so in that sense. And for volume charge distribution, your dq will be rho dV, okay, so which is all the similar to each other, but you are just calculating q or dq differently, okay. And then for point charges, you do summation, but for charge distributions, you do integration, okay, through a line, surface, or volume. All right, let's take a look on the first kind of example here on the calculating electric field for a line charge distribution, okay? So if you have line charge distribution as shown in the figure here, so this is a rod kind of shape, assuming the distribution density is uniform of lambda in there. So at a point where is a point P somewhere here, what will be the electric field produced by this distribution? Okay, so you'll see that for a small piece of the portion of this rod, right? So it will generate electric field here in this direction. If this is charge, the charge distribution is positive, then it's pointing away. So in that direction, derivative of E. And you're going to integrate through the whole body of this line, okay? So this guy will have an X component and then Y component, all right? So you can calculate the X component, integration to the X component first, and then the Y component. So to get the total electric field of the X and Y component. So this is the result here, but I'm going to show you guys how to get this result, okay? So let's see why the result is in this two forms here for the X direction and for the Y direction. All right. So from the figure, you can refer to the figure. From the figure, we know that for X direction, right? So we are going to say, all right, so for the E in X direction, or just take a small portion from the charge distribution. So for total derivative of E, that should be dq or k dq, right? K dq or q over r squared, right? And then r to the hat, okay? The unit vector hat. So this is a line distribution. So dq then equals to lambda times d of x, okay? A small section of derivative of x from the line. All right, then d of e is equal to k lambda dx over r squared r to the hat. So the x component dE of x, right? X component that will be k lambda dx over r squared. So if we are doing component, okay, then you are just really talking about what's the magnitude in that one. So you don't need an arrow on top of it. But magnitude, so this guy has a magnitude of 1, so then it's 1, okay? But then x component, you should have cosine of theta, okay? Theta is the angle showing in the figure. The vector r mixed with the horizontal, okay? And then derivative of E in the y direction should be k lambda dx over r squared by sine of theta, okay? So you have a sine of theta and cosine of theta. So for the overall electric field in the x direction, you'll do integration of derivative of x and through the line, okay? That should be equal to integration of k lambda dx over r squared cosine of theta and through the line, okay? So this then equals to k is a constant 1 over 4 pi times epsilon naught, right? Lambda is also a constant, so the density charge. So k lambda can go outside of the integration and leaves cosine of theta over r squared and then dx for the integration. Now, if you have a different x, your r will be different, right? Because r for its magnitude is the x squared, right, times the yp indicated in the figure, okay? And theta is also a function of x, okay? So we want to express cosine of theta and r squared in terms of x. So let's find the relationship first. So theta, and if you look at the figure, in the figure there, theta and, so let me just draw it here. So somewhere here, that's this yp, this is point P, so this length is yp. Okay. Yp should be a constant number if your p is fixed. And this is dx, okay? So this is where your x, in this case, is minus x, because this is you define this as your origin. And this is r. this angle is theta. Okay, so you can see from the figure here, theta is related to, this is x. Okay, the absolute value of x. All right. So in this case, tangent of theta, if you look at tangent of theta, okay, is equal to, tangent of theta is equal to yp over absolute value, or in this case, minus of x, because x is negative. Okay, so minus of x. Okay, because x is being negative. All right, so you can see then your x is equal to minus yp divided by tangent of theta, which is minus yp cotangent of theta. Okay. All right. So x equal to that. So dx then equals to minus, so derivative of that. So minus of yp is constant, so that comes out. Derivative of cotangent of theta. Okay. And derivative of cotangent of theta actually gives you, so minus yp here and times minus cos6 square of theta. Okay. And d theta. So this is according to chain rule of derivatives. Okay, so you can click on your PowerPoint slide. I have a table of the chain rules for derivatives shown there. Okay, so dx actually equals to that. Minus and minus becomes positive. Okay, positive and positive. So positive and positive. So dx then equals to that. All right. Now r is also, so this is r. R is also a function of theta. So if you relate r to theta, so sine of theta is equal to yp over r. Okay, so then r is equal to yp over sine of theta. Okay, so let's take these two into the integration layer first, and then we'll see if we need to worry about cosine theta after that. Okay, so e to the sub x is equal to k lambda integrations to the line, cosine theta of r square, r is this, so this one squared, so yp squared over sine theta squared. Okay, and dx is this guy, so that is times yp times cos6 square of theta and d theta. Okay, so 1 over sine theta is cos6 square. Excuse me. So then there's cancellation there. This guy and this cancel. Yp here will cancel out the square. So you still have yp down there. Okay. So then your integration becomes ky. Now yp is there over yp. Integration of cosine theta d theta. Okay. And then the theta will go from here, theta 1 through this angle of theta 2. Okay, so that's your integration from theta 1 and theta 2. Integration of cosine, actually, so this is integration of cosine d theta, so you don't have to worry about theta, okay? Cosine of theta. So that actually gives you sine of theta. So then this gives you k over lambda yp sine of theta from theta 1 to theta 2, okay? So then the result is, this becomes k lambda yp sine of theta 2 minus sine of theta 1. Okay, which is as the result showing in the PowerPoint. So if you go back to the PowerPoint, you'll see that. Okay, all right. And if you do, so if you check on the yp over sine theta, right? If you do yp over sine theta, that gives you r. So then sine theta over yp that gives 1 over r. Okay, so this could be also equal to, so sine over yp that is k lambda, right? 1 over r2 minus 1 over r1. Okay, so either this one or that one. Okay, as showing on the PowerPoint. Okay, and then next we are going to look at the y component. So this is what you have for the y component. Okay, x component. For the y component, you'll start with this guy and then integrate it. So e sub y is equal to integration of k lambda dx over r squared sine of theta. Okay, so similarly, and then through the line, you're gonna do k lambda, both are constant, it goes out of integration. Then you have sine of theta over y r squared. R squared will be now again this guy. So yp squared over sine squared. And dx will be here, this one again. Okay, dx is yp cosec square d theta. So again, cancellation here to here, and yp here cancels out the square there. So you again would have just ky over yp, and then integration from theta 1 to theta 2, sine of theta, d theta this time. Okay, so that becomes minus of cosine. So that equals minus of ky over lambda p, but cosine theta, right? So theta 2 minus cosine theta 1, that's your result. Which is the first expression you have on the PowerPoint slide, okay? And to get to the second expression for e sub y, you can do, so because yp is related to r as sine theta, right? So in this case, so then what you're gonna do is, so you are going to do manipulate the terms you have inside here. So this is going to be equals to minus ky lambda p, okay, cosine theta 2 times sine theta 2 over sine theta 2, okay, so that's still the same, minus cosine theta 1 sine theta 1 over sine theta 2, okay. So again, it's just similar to what we had there. Sine of theta 2 over yp is 1 over r2, right? And cosine theta 2 over sine theta 2, that's cotangent. Okay, so then it becomes cotangent of theta over r2. Okay, so this thing now becomes minus ky over yp and cotangent of theta 2 over r2, all right? For r2, 1 over r2 comes from sine theta 2 over yp because r equals to yp sine of theta. Okay, so if you do yp over sine theta 2, it gives you r2. Then minus cotangent of theta 1 over r1. Okay, so this is what you have. Minus there, or this one for the y. And then for the x, you are either having this one or having that one. Okay, so that's where the result comes from in the PowerPoint slide. So let's go back to the PowerPoint slide. And this is a table for the chain rule, generalized chain rule. Okay. All right. So then use that, you can apply what we just derived to this example 5.5 in the textbook. Okay, but quickly we are going to see that. So this is a uniform rod, have the charge distributions. Okay, and you're going from, so the whole rod has a length of L, so you can choose the center to be the origin. And this end will be -1/2 L, this end will be +1/2 L. Okay, so your integration should run through this guy to the other guy. Okay, and this you can use the result we got from the previous slide here. So in the x direction, you will have use either this one or that one. Okay, and then in the y direction, you'll use this or that. So it depends on what you are given. Okay, so in this case, you are looking for the electric field in the z direction. In this case, would be then the y direction you had in the previous case. So you're going to use a result from the y direction. Okay, so in that sense, E in the z, which is y direction, okay, which is going to be so z is the y direction in the previous example, and because of symmetric, you can see if you pick another one of the small piece over here, that because of symmetry, there should be another piece over here that result in another electric field in this direction and this direction. So these two will have their x components cancel, but add up in the z direction. So then you're going to apply the y component here. So this guy, starting with this one, with yp being z, so k lambda over z, okay, any cosine of theta 2 minus theta 1. So quickly, cosine theta 2 will be on this end, and then cosine of theta 1 will be on this end, theta 2 will be on the end. But theta 1 and theta 2, they are equal to each other, but then theta 2 will be the angle as 100 minus theta 1. Okay, so this guy is theta 1 here, or if you imagine this is the end here, so this angle and this angle are the same. So theta 2 being this one will be 180 minus that one. So cosine of theta 2 then will be actually this angle. That will be actually negative of cosine of theta 1. So at the end, you have 2 times of cosine theta 1. Okay, which you just check on this example in the textbook, it will end up with this result. Okay, so it's basically applying this one. Okay, but change the quantity accordingly. In examples 5.6, you can also check on that one. Okay, so it will be similar to what we have by looking at the scenario when L is equal to infinity. So this is infinity long one. Then this guy becomes dominant, right? This will be small, so then it becomes square root of L squared over 2 over 4. Then will be square root of that will be L over 2. So L will cancel, 2 will flip on the top. So then this is the result for that example. So if this is a cylindrical coordinate system, so then you have this as z direction, this is your r direction, radial direction. Okay, so similarly, you'll have now you have z direction as the original x direction. Okay, and then the r direction as the y direction, original y direction, but the expressions for the result will be the same. You're just changing the symbol to e sub z and e sub r in that sense. Okay, so we'll take a look on this example here. So this is the line charge again, but in this case, this is a z direction, and it's looking for what will be the electric field at this point P. Okay, so then we'll be using this result for that. Okay, oh, actually, sorry, we'll be using this result for that. So we are gonna to just use this expression. Okay, easy as k lambda 1 over r2 minus 1 over r1. So on this side, this guy here. And so let's go back. So for R1 and R2 in this case will be from here to here. And then R1 will be from here to your point of interest here. Okay. So look at this one. So if this is Z, So then this is R2 will be Z minus 1/2 of L. R1 will be Z plus 1/2 of L. Okay, so in that sense, then you are replacing R1 and R2 with these two. So then the result will be equal to, your EZ is going to be equal to K lambda 1 over R2 minus 1 over R1. Okay, and K lambda of 1 over Z minus L over 2 plus or minus 1 over Z plus L over 2. Okay, so with that, this is going to be equal to, so you're going to do the common factor at the bottom here. So K lambda of, you can put this all into the parentheses, but Z minus 1/2 of L and then Z plus 1/2 of L. So on top here will be Z plus 1/2 of L minus Z minus 1/2 of L. So Z and Z will cancel, minus minus become positive. So you'll have L on the top. Okay. So then that gives you K lambda times L, K lambda times L divided by Z squared minus, so Z squared minus L squared over 4. Okay, so A minus B times A plus B, so it'll be A squared minus B squared. So it says to show for that large values of Z, the expression for the electricity for the line charge on the Z axis approaches the expression for the electric field of point Q at the origin. Okay, so Z is greater, much greater than L. So then this term can be ignored because then at the bottom here, this is much larger, right? So this guy is ignored. So this is approximately K lambda over L Z squared. And then lambda times L will be the total charge. So then will be KQ over Z squared. Okay. So Z will be then the distance. So this is similar to KQR squared. Okay. In this case, if Z is much greater than L, then Z becomes R from the charge Q to the point. Okay. So that's what we have then. You kind of proved that. Okay. All right. So we'll stop here for today then. We'll come back next time. Okay. So see you guys.